Recording in progress.
Hi students, in this lecture I am going to discuss capacitors. Let us see list of concepts. So first we discuss definition part, then calculation of capacitance, combination of capacitors, force between the plates of a capacitor, energy stored in the capacitor, effect of dielectric on capacitance, and finally RC circuits. Let us say first what is a capacitor. It is a device which stores electric potential energy and electric charge. Let us see what is it in detail. Let us see. If you remember, while discussing Gauss law, so we have solved questions like two large conducting plates are placed parallel to each other. Two large conducting plates are placed parallel to each other and charges are given. Let us say charge is a Q and minus Q. So it is taken minus Q. Then calculate what is the distribution of charge on each phase. So these questions we have solved in Gauss law, right? Long back. So one is a Q, other one is minus Q. Now see what happens. We have discussed that on outer faces, charge will be always the same, which is equal to sum of the charges by 2. So here sum equal to 0, Q1 minus Q. Therefore, on outer faces, charge will be Q. And coming to inner face, Q. And this is minus Q. And here you can see between the plates, electric field is there. In the process of charging these plates, work is done. And that work stores in the form of electric potential energy between the plates. So now this combination is nothing but this is a capacitor, means it consists of two conducting plates. It consists of two conducting plates. When they are charged, then energy will be stored in the electric field. And you can see here electric field is only between the plates. It is only between the plates. So energy will be stored in that field. So now question comes, how to charge a capacitor? So when you are taking two conducting plates, let us say initially they are uncharged. Now the plate which is connected to high potential of the battery, that is called a positive plate. This is now high potential and this is now low potential. The plate which is connected to high potential of the battery is called positive plate, and the plate which is connected to low potential of the battery is called negative plate. See here what happens is electrons will flow from positive plate. So initially we have taken plates are uncharged, now connecting to battery. So now electrons will flow from positive plate through the battery and they will accumulate on negative plate. That means finally what happens is this is becoming positive charge and this acquires negative charge. And this continues until the potential difference between the plates is equal to that across the battery. So potential difference across the capacitor is equal to potential difference across the terminals of the battery, right? That means charge on the plates is proportional to the potential difference. I'm taking V for potential difference, not potential difference. That means if we connect a battery having more potential difference, then charge will be more. If battery potential is less, then charge will be less. So when we are charging a capacitor, we are connecting it to a battery. If battery having high potential, more charge will be there on the capacitor. And remember here, charge means it is not net charge, because on capacitor, net charge is always 0. You can see here, one is losing electrons and one is gaining electrons. That means a positive charge on this one and negative charge on this one. Both numerical values are same. One is plus, one is minus. Net charge is always 0. So when we are using the word charge on the capacitor, it is modulus of the charge on one of the plates. It is modulus of the charge on one of the plates. And this is depending on the potential difference. If it is more, it will be more charge on the plates. So charge is proportional to potential difference. And from this, if you want to write equality, we should write here one proportionality constant, that is C into V. And C is known as capacitance. What is C? C is known as capacitance. Capacitance or capacity. This is the capacitance of that capacitor. So capacitor means it is a device which stores electric potential energy and electric charge. Okay. And this is now it's a capacitance. And how it is defined means C equal to Q by V. So Q is a charge on the capacitor and V is a potential difference. That means coming to capacitance, whenever we want to calculate capacitance, first we have to imagine a charge Q on one of the plates. Then we have to calculate potential difference between the plates. Okay. Then ratio gives us capacitance. And see from this definition, we can say units for capacitance. It is a coulomb per volt, right? Charge is a coulomb and potential difference, that is volt. So coulomb per volt. And if you want dimension formula, and this is also written as Farad, which is the name of a scientist, Michael Faraday. Notation is a capital F. It is a scientist name, capital F. And coming to dimension formula, see how to get it. We know charge means current into time, potential. Earlier we have learned that potential energy equal to charge into potential, right? That means I can write here coulomb. That is, okay, charge is a Q. In the place of potential difference, I can write energy by charge. It is energy by charge, means it is a Q square. So Q square means it is A into T whole square. Energy. Energy means M L, sorry, it is M L square T power minus 2. Energy, right? It can be any type, energy, potential energy, kinetic energy. It can be any form of energy. Dimension formula same. M L square T power minus 2. Then see what we get. It is m power minus 1, l power minus 2, t square, t power minus 2. It becomes t power 4, a square. That is now dimensional formula. So let us now focus on how to calculate capacitance. Let us take now this special case, two large plates. You can say separation between them is very small compared to their dimensions, and this we are calling as parallel plate capacitor. It is known as parallel plate capacitor, writing simply PPC, parallel plate capacitor. Let us see now in this case what is expression for capacitance. Now see carefully what we are doing here. We are taking two plates. So we are knowing that capacitance equal to charge by potential difference. If you take more charge, potential difference will be more. That means capacitance is not depending on the charge. It is not depending on potential difference. Okay. So let us have assume here a charge Q. One is a plus Q, other one is minus Q. Then you can see here plus Q minus Q. Outer one 0, 0 plus Q minus Q. Right? That means now field is only between the plates. Now field is only between the plates. And we are knowing the field between the plates. Electric field is equal to sigma upon epsilon naught between the plates. Because due to each plate, field is sigma upon 2 epsilon naught. Just imagine here positive charge. Positive repels positive direction, right side. Negative attracts positive again, right side. Means both are in the same direction. So sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. Sum becomes sigma upon epsilon naught. This is electric field between the plates. Suppose separation equal to D between the plates. If separation is D, potential difference is equal to. So here field is uniform. Here field is uniform. That means field lines are parallel and equispaced. So here we take one assumption that at the edges, in fact, field is a curved, it is not uniform. It's actually curved like this at the edges. This is what we call fringe effect. What is it? It is known as fringe effect. And we neglect this fringe effect. So we are taking the field is uniform between the plates. So when field is uniform between the plates, potential difference equal to field into separation between the plates. That is sigma upon epsilon naught into D, right? And sigma is Q by A. So Q by A epsilon naught into D. So we got now potential difference. Now see here what we can write. Capacitance equal to charge upon potential difference. Right here. Charge upon potential difference Q by A epsilon naught into D. Q gets cancelled. It becomes now epsilon naught A by D, right? Remaining over QQ, epsilon naught A by D. That means if you observe carefully, capacitance of a parallel plate capacitor depends only on the dimensions. You can say dimensions of the plates, shape of the plates, and medium between the plates. So here we have taken epsilon naught. That means between the plates medium is it is air or vacuum. It is epsilon naught means. If you are keeping something between the plates, then this will change. So here we have taken between the plates, medium is air or vacuum. Next, coming to separation. It depends on the separation between the plates. Next, coming to area. If you take these are, let us say, circular plates, area will be pi r square. If you are taking square plates, area will be, it is like L square. So it is depending on shape of the plates. So depends on geometry of the plates, separation between the plates, and medium between the plates. If medium changes, capacitance changes. Okay. Next, see carefully here. We have taken one plate plus Q, other plate minus Q. In fact, we can take like this also. Instead of giving plus Q minus Q, instead of giving plus Q minus Q, charge Q is given to one plate, other plate no charge is given. See now what happens, distribution of charge. Outer plate Q by 2 and here also Q by 2. Inner plate Q by 2 and this will be minus Q by 2, right? This is now distribution of charge when Q1 0 given. Now, if you ground one of them, now ground this one, then see what happens. On outer face, charge will be 0. See, these questions already we have solved in Gauss law, right? So when we are grounding this plate, on outer face, charge becomes 0. So here also 0. Now for this total charge is Q. So it must be Q inside and this becomes minus Q. Okay. Now see carefully here what happened. Here plus Q minus Q. Distribution is 0, 0, Q minus Q. So if you want to calculate capacitance, either you can take plus Q minus Q, means giving plus Q charge to one plate, minus Q to the other plate and solving. Otherwise, giving one plate charge Q, now other one is grounded. In both cases, we have same configuration 0, 0, Q minus Q, 0, 0, Q minus Q. So we get again same result. So taking either like this or like this. So it is a completely our choice. Okay. Let us see now calculation of this capacitance in case of spherical capacitor. Now consider two coaxial spheres, conducting spheres, two coaxial conducting spheres. Let us take the radii A and B. So take now spherical capacitor. Inner one is A, outer one is B. If you remember, there is a potential difference between the conductors only if there is a charge on inner one, right? If you are giving charge to outer one, there is no potential difference. Potential difference is only because of the inner charge. So here also we can assume inner one is given Q, outer one is given plus Q. That is one way. Otherwise, giving inner one Q, now grounding the outer one. See what happens here. If a Q charge is given to inner one, this will induce here minus Q on inner face and plus Q on outer face. So when we are grounding this one, then on outer face, charge becomes zero. On outer face, charge becomes zero. That means now field is only in this region. Means energy is confined to only in this region. So potential energy will be stored only in this volume. Okay. I can say calculation of capacitance C equal to Q by V. Q already we have taken. Now we want between these two, what is the potential difference? See now potential difference. Potential difference we can write it as delta V is equal to minus integral E dr, right? See what is a field in this gap. In this gap, a field is because of this charge. So when you are taking the field because of a conducting sphere outside, we can assume the entire charge at its center. It is just like due to point charge. Then see what we can do here. E value kq by r square into dr. Okay. So now we want to take here limits. So we are knowing that field is readily outwards. And along the field, potential decreases. That means potential of outer one is less compared to that of inside. Okay. Let us focus now here. Limits. It is A to B. See what we get. KQ constant take outside and having here minus outside. 1 by r square dr. It is minus 1 by r. That minus minus gets cancelled. It's a kq into 1 by r. Now take limits. It is A to B. Then see what we get. See the substitution part. Right. If you substitute values there, see we are going to get kq into 1 by b minus 1 by a. And this value will be negative, right? A minus b value negative because we have taken A to B and we want only potential difference. That means see what is the difference, okay? It is not outer minus inner. If you are taking the modulus value, that potential difference equal to KQ, KQ B minus A upon AB. So potential of the inner one minus potential of outer one. That is now this value. And this is giving us potential of outer one minus potential of inner one. Okay. So V is the potential difference. After having potential difference, now we have to take C equal to Q upon V. Then see what we get. Q gets cancelled. Remaining is now take Q V value K Q B minus A by AB. So Q gets cancelled. In the place of K, 1 by 4 pi epsilon naught. So it becomes 4 pi epsilon naught into AB by B minus A. This is now capacitance of a spherical capacitor. This is capacitance of a spherical capacitor. Let us now focus. If we consider cylindrical capacitor, it is cylindrical capacitor. So take two cylinders which are coaxial. So consider two cylinders which are coaxial. Right, let us now focus. So it is now. So taking two cylinders which are coaxial, which are coaxial. Let us say the inner one is given charge, or let us say charge per unit length, that is lambda, inner one. Outer one is given minus lambda. So either we can take giving charge only to inner one and grounding outer one, that is one way. Otherwise giving plus and minus, both are same. Now focus the gap between the cylinders. So here we are taking now length is very large. So when you want to find the field in the gap between the cylinders, field is just like due to a long infinite wire, right? So field is 2k lambda by r. So taking at a distance r from the axis, field equal to 2k lambda by r. So now we want to find out potential difference between the cylinders. Okay. Again, take here delta V equal to minus integral E dot means E dr, E value 2k lambda by r into dr. See what we get. 2k lambda constant 1 by r dr. It is ln. If inner one is A and outer one is B, the radii A and B. Now taking limits here, it is ln B by A. This is what we are taking potential of inner one minus potential of outer one, because potential of inner one is a high. That's why I'm taking potential of inner one minus potential of outer one. So let us call it as V. So V equal to 2k lambda ln B by A. Now capacitance equal to Q by V. So it is a Q. Q means how much means it is lambda into L, right? Charge is lambda into L upon V value 2k lambda ln B by A. Lambda gets cancelled. It is now, see what is the value. In the place of k, 1 by 4 pi epsilon naught, 2 gets cancelled here. It is a 2 pi epsilon naught L upon ln B by A. So like this, we can calculate capacitance for each and every capacitor. That means just assume there is a charge Q and outer one is grounded. Otherwise, give plus Q and minus Q. Same logic here also, giving plus lambda minus lambda. Otherwise, giving here plus lambda. Outer one is grounded. So both are equivalent. Okay. So next step is calculation of potential difference. And once we know potential difference, charge upon potential difference gives capacitance. So for spherical capacitor, it is a 4 pi epsilon naught AB by B minus C. For cylindrical capacitor, 2 pi epsilon naught L upon ln V by A. Right?